Hello everyone, my name is Bai Chen, currently a second-year PhD student from the Chinese University of Hong Kong, supervised by Professor Yu. Previously, I received my bachelor's degree from the University of Electronic Science and Technology of China in 2020. My research interest lies in design space exploration and hardware and software co-design. Today, I'm going to present the topic Boom Explore RISC-V Boom Microarchitecture Design Space Exploration Framework. First of all, I would like to thank all of my co-authors for their discussion and brainstorms in this work. And we expect there will be a lot of researches in this domain to further improve microarchitecture design space exploration in RISC-V. My presentation will be divided in 4 parts. First, I will introduce the basic background and some prior knowledge. For the second part, I will introduce preliminaries and problem formulation. For the third part, I will detail in Boom Explorer, and for the final parts, I will present experiment results. As we can see, we have nowadays lots of ICs in the world, and here I just list most of them, most popular of them. For example, we have x86, we have ARM, and we have RISC-V. And RISC-V recently has gained a lot of attention from academia and industry for 2 reasons. First one, it is open source. For second, it is free and we can easily get numerous designs. And in this work, we have a second keyword that we call it microarchitecture. Microarchitecture is an implementation of an IC in a processor. And then it can affect the performance, power dissipation, and area of the processor. Because we have some kind of mechanisms like chisel, so we can easily parameterize our structures of cores. Like we can parameterize cache structures, decoders, execution units, LSU, key buffers, queues, and stacks, so on and so forth in a processor. So that means we can construct different microarchitectures. And because different microarchitecture can affect the performance, power, and the area of the processor, so it is a tough question that it is really tough to answer what kind of microarchitecture that can achieve a goal value on these 3 metrics. And then one more thing should be noticed that they are discrete variables in this design space. So based on this question, we have different solutions. In industry, it is often rely on engineering experience of CPU architects. And in academia, previous researchers use different black box models, like they use the AM-based model, regression-based model, or even novel initialization plus machine learning methodologies to solve this problem. But both of these methods, they have some obvious faults. Like for industry solutions, it lacks scalability for newly emerging processors. And for academic solutions, previous arts, they fail to embed priority of microarchitecture designs to algorithms. And one to notice is that previous researchers, they use cycle accurate simulators. And most of these simulators, they just only provide performance value. So they just only build black box model to characterize the performance of the processor, but fail to build a black box model to characterize the power model. So the academia lacks discussions on striking a good balance between the performance and the power dissipation of a microarchitecture design. Based on the problem and these limitations, we present the Boom Explorer to solve this problem. And our research target is RISC-V Boom, which is a 10-stage pipeline RISC-V machine. And we choose this design for 2 reasons. First, it is fully compliant with RV64GC IC. So that means RISC-V Boom can execute most of RISC-V instructions. It is representative. And second, it is an out-of-order design and can be complicated enough to conduct design space exploration research. As you can see in this figure, the Boom architecture can be composed into 4 different parts. The fetch units fetch instructions from Iccad and put these instructions to the fetch buffer. And the fetch buffer is a buffer that can decouple a front end and the instruction decoding unit. And in the IDU, we can equip different numbers of decoders and logics. And because this is an out of order design, so it can execute instructions in an out of order manner. So it has a reorder buffer. And in the execution units, it has different issue slots. And if some instructions will be interactive with decatch, so there's an ISU and 2 queues that couple the EU and LSU, that is STQ and LDQ, which is short for store queue and load queue. So based on this architecture, our design space can be formulated as shown here in this table. So we have fetch with REST entry for branch predictors, and we even equip with different structures of decatch and issue width. So based on this microarchitecture design space, not all microarchitecture is legal, so we should obey this rule or this specification of Boom design. If we cannot obey it, it will fail to synthesize. And based on the microarchitecture, we give the definition of this terminology. Here in this work, microarchitecture is a combination of candidate values defined in the design space of RISC-V Boom. Because different combination of candidate values can construct different microarchitecture. And our research target is power and performance. So in power, we submit dynamic power, short circuit power, and leakage power, because we want to characterize the full power dissipation of RISC-V Boom. And for the performance, we use clock cycles to denote for simplicity, because every Boom design will run the same benchmark suite. So that means they are faced with the same number of instructions. Then, and how can we define a design that strikes a good balance between power and performance? So we give the formal design of parallel optimality with respect to equation 2. Here, we use the figure to visualize the equation 2. As you can see in figure 2, this is a 2-dimensional space, and the orange circle is a reference point, and the green circle, you can see that they are dominated by purple circles. And as you can see, none of purple circle is dominated by any other point in this 2-dimensional space. So we say that purple circles, they form the parallel optimality along this 2-dimensional space. And till this now, our problem formulation can be like this, can be formulated. In the design space D, find a series of microarchitecture X that form the parallel optimality among the power and performance. And it can be expressed as this kind of mathematical expression. So based on the definitions and our problem, we use Boom Explorer to solve it. And I have summarized 3 highlights that how we solve it. As you can see in the left figure, it shows the overview of Boom Explorer. And in the right figure, the first highlight that we embed prior knowledge on constructive experiment design. Unlike previous methodology, they just only build black box model. They do not why their black box model works, and even don't know how they improve their black box model. So here we combine prior knowledge on RISC-V Boom microarchitecture and an active learning algorithm. So we think that this can form a representative initial set. And for the second highlights, we use a deep Gaussian process with deep learning as our surrogate model. And because Bayesian optimization can deal with very hard to evaluate functions. So DQGP as a powerful and robust black box model, this can be a good choice. And for the Bayesian optimization framework, we formulate a good acquisition function that is expectation improvement on parallel hypervolume, or which is short for EIPV, and to deal with the multi-correlated problem. And as you can see, first we use micro-AL to sample the most representative initial set to initialize our DKLGP, the black box model. And then the DKLGP will try to interact with the Boom design space and the Villa-side flow to interact in via the Bayesian optimization framework. And with EIPV to deal with multi-correlated objectives, they can output a good series of microarchitecture that achieve good that can achieve good balance between power and performance. Here the correlated multiple objective means that power and performance, they are negatively correlated. If we want to increase the performance, the power dissipation will also be increased in normal cases. So how can we embed prior knowledge on transdriver experiment design? In the left figure, as you can see, we find that if we sample microarchitectures with respect to decoding width, or that means if we fix the decoding width with one value and sample the microarchitectures along this when the decoding width is fixed, so we can see that they form the potential parallel curve along this two-dimensional space, the power and performance space. As you can see, when the decoding width equals to 5, the performance will be increased, obviously. On the other hand, the power dissipation will be increased. If the decoding width equals to 1, it will be much power efficient. Because decoding width, which resides in IDU, it can decide the instruction throughput. So this can be a good impact to the balance between power and performance. And on the right figure, we give the backbone of TED. As you can see in line 3, TED tries to maximize the intra-diversity of trace matrix with respect to samples. So we combine with the priority and TED to formulate our micro-AL as algorithm 2. As you can see from line 2 to line 5, we partition the design space with respect to decoding width as potential clusters. And then we use TED to sample in each clusters. And we believe that the samples formulated by micro-AL can be very representative at this design space. And for the black box model, the DKLGP, first we introduce Gaussian process. Gaussian process can be extracted with expression with respect to equation 3. And we give the noise value that is with respect to a normal distribution. And when we are given a newly sampled X, the predictive joint distribution can be obtained with equation 4 here. So it has a closed form. And in fact, in Gaussian process, we are often confronted with what kind of kernels we can choose, and what kind of kernels the Gaussian process can perform the best. So this is a tough question, and we let the neural networks do this workload. So we form the deep kernel learning in Gaussian process. And equation 5 here, it means that we use neural networks to try to approximate a suitable kernels, and 5 denotes the nonlinear transformations residing in neural networks. Here, this figure visualizes what is a DKLGP, and here it uses 3-layer, it stacks 3-layer to encode the input vectors to the hidden states, and hidden states will try to be approximated to the suitable Gaussian kernels. And through this way, we can build suitable Gaussian processor functions to characterize the power and performance of microarchitectures. And as I introduced the created multi-objectives, we can just build a math model like equation 6 to as our target. However, because this is creating multi-objectives, if we want to increase power, if we want to increase performance, the power will also be increased. But in fact, we want power to be more efficient. That means it can even be decreased. So we formulate equation 7 here, and the equation 7 calculates the parallel hypervolume. And what is the parallel hypervolume? And this figure shows the meaning of parallel hypervolume. In the right figure, as you can see, the dominated red circles are in orange region, and the blue circles, they are currently explored parallel optimal sets. If a newly explored parallel microarchitecture is found in figure B, so we can see there is a gain in the parallel hypervolume, and it is shown in the area of the green region. So the green region is the EIPV, or the expected improvement of parallel hypervolume, and can be formulated as equation 8. By further decomposing the power and performance space as grid cells, we can formulate equation 9 for easy calculation. So we use EIPV as our surrogate model, and we embed EIPV as the Bayesian optimization framework. So our end-to-end flow of Boom Explorer can be formulated like this. First, we use microAL to sample the most represented microarchitecture designs, and then we use EIPV as our surrogate model, and we use DKLGV as our surrogate model, and use EIPV as our acquisition functions. So through this iteration manner algorithm, Boom Explorer can find microarchitecture that can achieve a good balance between power and performance. For the experiments, we use ASAP 7 PPT cells to conduct the experiments, and it is focused. It is targeted at 7 nanometer technology PDK, and we use Janus, VCS, and Primetime PX to do the synthesis, simulation, and power evaluation respectively. Because we cannot evaluate each microarchitecture in the whole microarchitecture design space, so we build an offline data set, which is composed of 994 RTL designs, and each of them are running at 2 GHz. And then we use representative benchmarks to do the evaluation, because these 4 benchmarks, they are complete to all RISC-V instructions, including register to register instructions, register to memory instructions, branch instructions, so on and so forth. And for baselines, we compare with previous arts, and we also compare with the high-level synthesis work. Although the starting point is different, their work is proven to be transferable. And we also compare with machine learning, traditional machine learning models like SVR, XGBoost, random forest, so on and so forth. And the whole evaluation flow is shown here. We leverage chipyard to do the whole VLSI flow, and use this flow to provide performance value and power value. So this figure gives the predictive parallel optimality by different algorithms. The green plus symbol denotes the design space, and the orange cross shows the real parallel. And you can see that the red circle is denoted Boom Explorer, but is denoted by Boom Explorer. And these microarchitectures are found by Boom Explorer, and you can compare with other microarchitecture designs. And through this visualization, we can see that the microarchitecture found by Boom Explorer is far more closer to the real parallel. For more comparison, we compare this algorithm with normalized ADRS and normalized ORT. ADRS is formulated as equation 10. It calculates the distance between the real Pareto to the predicted Pareto. So as you can see, Boom Explorer outperforms other Rs. And we also compare Boom Explorer with and without micro-AL. As you can see, without micro-AL, the performance decreases. And we also compare Boom Explorer with a 2-wide boom. So as you can see, this 2-wide boom is published by Berkeley. And we report the average power and the average clock cycles here. We also evaluate these two designs on more benchmarks to fully conduct further research. As you can see, the Pareto design outperformed the 2-wide boom by average power and clock cycles. So why our Pareto design succeed? Because of 3 facts. First one, we assign more hardware resources to LDQ and SDQ. As I introduced, LDQ and SDQ are 2 important queues that can solve the bottleneck between the EU, between the core and the D cache. And then we assign larger associative set and MSIHR entries for D cache to alleviate data access conflicts. For third part, we assign less resources for REST and BTP. I think this is application driven because in our evaluation applications, there will be not too many branch instructions. So we can decrease power consumption on this point. So why our Boom Explorer can find the design? I think because of 3 factors. First, micro-AL, because we embed prior knowledge on microarchitecture design. So it is specific. For second, it is a robust and non-parametric black box model. For third, I think EIPV is a good formulation to deal with multi-correlated objective problems. So because of these 3 effective methods, our Boom Explorer can succeed and it performs better than any other algorithms. So these are all my presentations. Thank you.